January 15th, 2025. 4,000 astronomers. National Harbor, Maryland. The man running operations for the most powerful telescope ever built steps to the microphone and says 5 words. It's extremely worrisome. 3 years into a mission breaking every performance record, and the person responsible for it used those words in public at the world's largest astronomy conference. This is what he meant, and why almost nobody outside that room reported it. The James Webb Space Telescope began its journey on December 25, 2021, leaving Earth behind atop an Ariane 5 rocket. By mid-2022, it was fully awake at the edge of our solar system's shadow, 1.5 million kilometers from home. 4 instruments, NIRCam, NIRSpec, NIRIS, and MIRI, came online, each one pushing the boundaries of what astronomers could see. The segmented primary mirror, stretching 6.5 meters across, gathered light with a collecting area 6 times greater than Hubble. Its optics, diffraction limited at 2 microns, delivered images twice as sharp as the original requirement. Galaxies emerged from the darkness, some only 400 million years after the Big Bang, their spiral arms and dust lanes revealed in colors never seen before. Demand for Webb's capabilities has outpaced every expectation. In the 5th cycle of proposals, nearly 3,000 research teams competed for a slice of observing time. Only 254 projects could be chosen, a selection rate of just 1 in 11. The accepted programs target everything from the atmospheres of TRAPPIST-1's rocky worlds to the deepest reaches of cosmic history. Each cycle's call is oversubscribed by nearly a decade's worth of science per year, a measure of hunger that has only grown as the telescope's performance exceeds what its designers promised. The telescope's early results have already rewritten textbooks. JWST's instruments have captured the first robust spectra of exoplanet atmospheres at cosmological distances. Its images have forced theorists to reconsider how quickly the universe formed stars and galaxies. Over 1,200 peer-reviewed papers have appeared in less than 3 years of operations, a pace unmatched by any mission of its kind. And yet, as Jennifer Lotz, director of the Space Telescope Science Institute, told the assembled astronomers in Maryland, JWST is not even close to hitting its peak science or demand. The community's appetite for discovery is growing, not shrinking. The telescope is ready. The question now is whether the support for those who interpret its findings will keep pace. NASA's official budget documents lay out the numbers with no fanfare, but the figures themselves tell a story of contradiction. For years, the James Webb Space Telescope operated on a baseline allocation of $187 million per year. That line item, set back in 2011, is split between 2 essential functions. About $127 million covers the cost of keeping the telescope running, its ground systems, routine instrument support, and flight operations. The remaining $60 million is not for hardware, but for the science grants that fund the researchers, postdocs, and students who turn raw data into published discovery. This split, established before the telescope ever launched, shaped both the mission's capacity and its promise. It is a formula designed to ensure that every photon Webb collects can be traced all the way from the detector to a scientific result. But as the telescope began to deliver, the fiscal ground shifted beneath it. The enacted budget for fiscal year 2026 drops the total to $140 million. Operations funding remains nearly steady, but the science grant envelope contracts sharply. The proposed White House budget for fiscal year 2027 goes further, calling for a 47% reduction in the science grant line, down to about $31 million per year. The technical operations budget, meanwhile, is held at roughly $115 million, just enough to keep the observatory working, but not enough to sustain the full breadth of scientific analysis. These numbers appear in NASA's Congressional Budget Justification, where the James Webb Space Telescope line item is broken out under Space Science Observatory. The documents show a pattern. The mirror and instruments are protected, but the people and programs needed to interpret the data are being pared away. Over the past 4 cycles, the grant success rate for general observer proposals has hovered around 30%, with awarded budgets ranging from $100,000 to $2 million per program. The proposed cuts would shrink the pool of funded projects, limit the number of new papers, and slow the pace of discovery. The archive will continue to grow, but the capacity to turn those observations into knowledge is being systematically reduced. The paradox is now written into the budget itself. On January 15, 2025, the annual town hall at the American Astronomical Society meeting took an uneasy turn. Tom Brown, head of the James Webb Space Telescope mission office, addressed the crowd with a warning that cut through the usual optimism. He said it was extremely worrisome that the projected staffing shortfall for their full-cycle support staff could compromise the mission's ability to process the growing data volume coming from the next cycle. The number behind his concern was clear. 110 full-time equivalent positions at the Space Telescope Science Institute were at risk if the budget ceiling was not raised. An internal memo circulated just weeks before spelled out the consequences. 40% of those at risk were pipeline engineers, 30% were review panel coordinators, and the rest covered anomaly response and outreach. The scale of the problem was a public risk. Brown listed the functions on the line. Proposal review panels faced a 30% reduction in senior reviewers, which could drag out the selection process for new science. Data analysis teams, already stretched, would lose a quarter of their engineers, delaying the release of calibrated data by weeks. Anomaly resolution staff would be cut by 2 full shifts, doubling the time needed to respond to critical technical problems. Even the infrastructure that assigns digital object identifiers and tracks citations for new papers, the backbone of scientific credit, was set for a 15% budget cut. Those cuts would directly threaten scientific credit. Jennifer Lotz, the director of the Space Telescope Science Institute, echoed the gravity of the moment. She said the James Webb Space Telescope is not even close to hitting its peak science or demand. She outlined 3 priorities: keep user support grants robust, accelerate development of automated data pipelines, and secure supplemental funding. Her message made the priorities clear, but the underlying message was unavoidable. The mirror is protected, the discoveries keep coming, yet the workforce that turns those discoveries into knowledge is being quietly thinned. As the meeting adjourned, the sense of alarm was no longer abstract. For the first time, the numbers and names were public, and the risk was immediate. The threat was to the workforce, not the telescope. In the spring of 2024, a letter from Patrick Slane, director of the Chandra X-ray Observatory, landed on desks across NASA headquarters. The words were measured, but the warning was unmistakable. Chandra, the world's only flagship-class X-ray observatory, had just received a Tier 1 rating in NASA's Senior Review, the highest possible endorsement, reserved for missions deemed essential to the scientific enterprise. Yet the budget documents told a different story. The fiscal plan from 2024 to 2029 mapped a plunge from $68.3 million per year to just $5 million by the decade's end. Not a managed drawdown, but a cliff, enough to keep the spacecraft alive, but not the science teams, the data pipelines, or the proposal review panels that turn photons into discovery. The contradiction was not lost on the scientific community. Chandra's Tier 1 status was supposed to guarantee stability, but the numbers set in motion a chain reaction that no peer review could halt. The first wave of cuts arrived as a reduction to $44 million, labeled as cost-saving measures. The following year, the figure dropped to $30 million, then to $12 million, with the remainder earmarked solely for archival preservation. By 2029, only the skeleton of a once vital mission would remain. Inside NASA's Goddard Space Flight Center, the effects rippled outward. Proposal review teams disbanded, data analysis pipelines were quietly mothballed, and unique calibration facilities were shuttered or repurposed. 13 buildings closed their doors. High-value equipment, built for the rarest X-ray calibrations, was dismantled or shipped to storage. Within 6 months of the first major cut, about 20% of Chandra's workforce had accepted buyouts or left for other positions, taking decades of institutional knowledge with them. The loss was not just technical, it was generational. Patrick Slane, facing the prospect of a forced closeout, wrote that Chandra remains the only facility capable of high-resolution X-ray spectroscopy for distant galaxy clusters. His public letter, circulated in March 2024, challenged the logic of the cuts point by point. The response was immediate. The hashtag Save Chandra campaign gathered over 5,000 signatures in its first 2 weeks, drawing support from university consortia and international partners. But advocacy could not reverse the administrative machinery already in motion. The science analysis budget was halved, then halved again. Government shutdowns in late 2025 compounded the problem, forcing emergency relocations and further attrition. The consequences reached beyond the loss of a single mission. Chandra had been producing roughly 400 peer-reviewed papers each year, supporting a community that stretched from graduate students to Nobel laureates. The sudden contraction forced research groups to abandon long-term projects, and the flow of new results slowed to a trickle. For early career scientists, the abrupt loss of funding meant lost fellowships, cancelled postdoc positions, and a wave of departures from the field. The lesson was clear. A mission can survive in the archive, its hardware intact, while its scientific heart is quietly starved. The mirror keeps collecting photons, but the workforce that interprets them is allowed to erode. The fate of Chandra stands as a warning, not just for its own community, but for every flagship observatory that follows. As Slane put it, without the people and the infrastructure to analyze the data, the discoveries remain locked in the archive, and the promise of the mission is left unfulfilled. On April 3, 2026, as headlines celebrated the safe return of Artemis II from lunar orbit, a very different story appeared in the Federal Register. The White House Office of Management and Budget released its fiscal year 2027 proposal. It would cut NASA's Science Mission Directorate from $7.25 billion to $3.9 billion, a 47% reduction. Every major science division faced cuts, but the most immediate consequences landed on the workforce behind the James Webb Space Telescope. More than 2,000 civil service positions across NASA's science programs were tagged for elimination, the largest proposed single-year reduction since the Apollo drawdown. The budget would terminate over 50 missions, from planetary probes to Earth science satellites. For JWST, the hardware would remain untouched. The mirror would keep collecting photons at L2, and the instruments would keep transmitting data. But the support system, the people who review proposals, calibrate the data, and write the papers, would lose half its funding in the science grant line. Casey Dreyer, policy director at the Planetary Society, called the proposal a textbook example of a budget crafted without regard for scientific continuity. In his words, the proposal reads like a sloppy, unprofessional copy-paste of last year's budget, complete with factual mistakes. The document mistakenly cancelled the Mars sample return mission, which had already been terminated, and it cited the wrong fiscal year for JWST funding. Dreyer's critique echoed through the science community, fueling a sense of disbelief that such a sweeping rollback could follow so soon after one of NASA's most visible successes. Within days, the shockwaves reached Capitol Hill. Representative Randy Babin of Texas announced, "This budget will be rejected again." Senator Jerry Moran of Kansas described it as a staggering retreat from American leadership in space science. The numbers remained a $24.4 billion top line for NASA, still far below the agency's own request, and a science portfolio on the chopping block. The House Committee on Science, Space and Technology scheduled its appropriations vote for May 13, 2026, with the fate of JWST science workforce hanging in the balance. Inside the Space Telescope Science Institute, the mood turned from concern to urgency. Staff who managed JWST data pipelines, proposal review boards, and anomaly response teams began to see their own positions listed in risk assessments. The Institute's internal projections showed that, if enacted, the reduction could force the loss of up to 110 full-time equivalents, engineers, analysts, and coordinators whose work transforms raw detector output into discoveries. The timing could not be worse. Cycle 5, the most competitive round of JWST proposals yet, was set to begin in July 2026. 8,000 hours of observing time would be awarded to 254 programs out of nearly 3,000 submissions. The archive would swell with new spectra and images, galaxies at the edge of cosmic dawn, exoplanet atmospheres, black hole candidates, and Hubble tension targets. Yet the pipeline to analyze, publish, and debate these results was being systematically narrowed. The lesson from Chandra was fresh in every mind. There, a Tier 1 mission had been reduced to archival status not by hardware failure, but by the loss of the scientific workforce. Now, the same pattern threatened to repeat at Webb. The archive would continue to grow, but discoveries risked remaining locked in digital storage, unstudied and unpublished. As Neil Reed warned in a public statement, the telescope keeps working, but if you cut the people, you cut the science. The discoveries don't interpret themselves. The debate over the fiscal year 2027 budget sharpened as the May vote approached. The question was no longer whether the James Webb Space Telescope could survive as a machine, but whether the United States would sustain the human capacity to extract meaning from its greatest observatory. The mirror would endure. The risk now was to the minds who read what it finds. Cycle 5 opens with 8,000 hours of observing time, a prize divided among just 254 research programs. The list reads like a survey of the frontiers of astrophysics: TRAPPIST-1's habitable zone planets, early universe galaxies less than 300 million years old, massive black hole candidates, and the precise measurements needed to resolve the Hubble tension. Each target represents months of preparation and review. Some, like the TRAPPIST-1 atmospheric studies, require coordinated campaigns across multiple instruments and international teams. Others, such as the deep field imaging at redshifts beyond 12, push the telescope to its design limits, hoping to catch the faintest signals from the first generations of stars. The demand for these hours is overwhelming. Nearly 3,000 proposals competed for a place in Cycle 5, but only a fraction could be chosen. The rest, years of work from scientists around the world, remain on hold, waiting for another chance. For those selected, the stakes are immediate and concrete. Without stable funding for data analysis and publication, even the most promising observations risk stalling at the download stage. Spectra of exoplanet atmospheres, once heralded as the next leap in biosignature detection, could linger in the archive, unpublished and unexamined. The archive will expand, but the discoveries it contains may never reach the scientific record. The science is queued, the photons are captured, but the pipeline to knowledge is narrowing. Across the halls of the Space Telescope Science Institute, the reality of budget attrition lands not as a headline, but as a series of personal reckonings. A postdoctoral researcher, newly arrived from overseas, finds her contract terminated with 3 months' notice. Her project, once greenlit for JWST Cycle 5, is now shelved indefinitely as the grant line evaporates. A principal investigator, years into a study of early universe galaxies, cancels the final phase of analysis when supplemental funding falls through. The team disperses and the data sit untouched in the archive. These departures are not easily reversed. Unlike hardware, lost expertise cannot be ordered back on demand. The review panels that once drew on deep institutional memory now scramble to fill seats with less experienced volunteers. Pipeline engineers, lured by more stable work in private industry, take with them the undocumented knowledge that kept the data flowing. Rebuilding a scientific staff takes years, sometimes decades. Each wave of attrition leaves a scar that no emergency appropriation can quickly heal. The question left hanging is not whether the telescope will keep working, but how much of its promise will remain locked away, waiting for interpreters who may never return. Today, the universe sends more secrets than ever, but the people who decode them face shrinking support. As Jennifer Lotz warned, the James Webb Space Telescope has not reached peak science or demand, yet the pipeline narrows. The real risk is not hardware failure. It is a slow erosion of human capacity. When discoveries sit archived and unstudied, knowledge itself goes dim. In this silence, the loss is not just scientific, it is generational. What do we choose to leave unexplored?